Okay, in this fourth episode of Newton's Laws, we're going to be looking at how to use free body diagrams and graphs to help determine if the forces are balanced or unbalanced. Okay, so in this one we have three different velocity time graphs, and we want to figure if the forces are balanced or unbalanced. Now, if the velocity is changing, if it's increasing or decreasing, then we would expect there to be an acceleration present, and therefore an unbalanced force must be present. So in the first one, the velocity is the same the whole time. It's staying at some value. Therefore, the forces are unbalanced, are not unbalanced, so there are no unbalanced forces around. And the reason for that, again, is we are moving with constant velocity. Now, that's assuming there's no change of direction. We're moving along a single line. In the next one, we are decreasing. We're going from some larger number to a smaller number. Since that's happening, there must be an unbalanced force present to make a slowdown, and that would be changing our speed, in this case decreasing our speed. In this one we're starting at 0, it looks like, and going to some larger number, so therefore there must be an unbalanced force present. We are getting faster. Again, we're changing the speed. In this case we're increasing the speed. In our first case we were decreasing the speed, our second case. Now, ways to figure out if the forces are balanced or unbalanced are one is to look at all the forces acting on an object and sum them, add them together. So you see this a lot, sigma F, add summation of forces, net force. There are lots of different ways to describe that idea. Net force, again, just means add up all the forces. Whatever's left over is the net force. Now this 40 up and the 40 down are going to cancel. So that makes the net force 10 newtons to the left, and therefore the object will accelerate. Now, if it's currently at rest, it will speed up to the left. If it's currently moving to the right, it would slow down. If that force is still there as it slows down and stops, it will start moving in the opposite direction. Now this one cancels with this one, so the net force is 0, and therefore no acceleration. Now that doesn't mean the object's not moving, it just means it's not going to speed up or slow down or change direction. In this one we have 40 up and 25 down, so this gets rid of 25 of that, but leaves 15 behind. So we have 15 newtons up, and therefore there will be acceleration. Now, it might be that, again, we are accelerating upward. It might be that as we move downward, we're starting to slow down, but there will be an acceleration, a change of our state of motion. Okay, so analytical during a discussion looks at the diagram in number object 6b here. This is the one that we're talking about. Could be this dot diagram, which would indicate constant velocity. Dots are equally spaced, moving in a straight line. Anna's partner would object, saying, no, the could not have any horizontal motion because there are only vertical forces acting on it. In this case, it's Anna who's right. Okay, forces are not required to keep an object in motion. Right? They are required to change the state of motion. So as long as the object was already moving to the right, these balanced forces that we see in B would simply mean that it would maintain that constant speed and direction. So it would maintain constant velocity if it was already moving. This is a common misconception. A lot of people feel there has to be a force to keep things moving forward. Not true. Again, inertia is the property of matter which allows things to stay moving even though the forces on it are balanced. Then in number 8, Aaron again asserts that the object 6A must be moving to the left since the force is leftward. Again, he is not right. It might be moving to the right and slowing down. It's current state of motion, we have no way of knowing its current state of motion. We only know that it's not going to be maintaining exactly that same state. It's not going to move at constant velocity. It's also not going to stay at rest. He is correct. If it had been at rest, it would start moving to the left because the net force would be to the left. But if it had been moving to the right, it would be slowing down. If it had been moving at some angle, then it would have been changing based on that overall force. So we need, the forces do not tell us the current state of motion. They tell us how much it will change by. And then 9, which ones could be moving to the right? Well, circle all that apply. Which ones should I circle? Again, I'm just going to make one big circle. There's nothing about the free body diagram that tells us the current state of motion. They could all be moving to the right. It would tell us whether it was going to speed up, slow down, or change direction. The free body diagram does not tell us the current state of motion. It indicates the change of state of motion. There we are, back to that word change, delta. It's all the way through the concepts of physics. It's what is the change of something. Here, the free body diagram will tell you what is the change of the state of the object's motion. That's it for this one. We'll see you in the next one in a little bit.